So we're going to continue looking at optimizing areas and perimeters. So for our next example, a farmer is creating a fenced yard. She has 900 meters of fencing. Will a rectangular or circular arrangement maximize the area? So first let's start with our rectangular arrangement. We know if we have a rectangular arrangement, to maximize the area, our arrangement will be a square. And since we have a square, we know all four sides are equal in length. So our perimeter is equal to 4 times L, or 4 lengths. In our example, we have 900 meters of fencing. Taking both sides of this equation and dividing by 4, we end up that each side length will be 225 meters. So this gives us our dimensions for this square are 225 meters by 225 meters. And that tells us that our area, which is equal to length times length, or length squared, is 225 squared, which gives us an area of 50,625 meters squared. So that's for our rectangular arrangement. Let's go now to a circular arrangement. So this time we have a circle. And perimeter is the same thing as circumference when we talk about a circle. The distance around a circle we call circumference, and that's equal to 2 pi r. So this time we have 900 equals 2 pi r. So if we want to find the radius of this circle, since we have 2 pi times r, we're going to divide both sides by 2 pi. And we get that the radius of this circle is approximately equal to 143.2 meters. So the dimensions of the circle, so the dimensions are a radius of 143.2 meters. And if we want the area of the circle, if we look back at our formula sheet, that's pi r squared. So this is pi times 143.2 all squared, which gives us approximately an area equal to 64,457.8 meters squared. And if you look at the two areas that we end up with, we see that a circle will optimize the area given a fixed perimeter better than a square. The second thing we're going to look at is optimizing with restrictions. So for example 2, a rectangular garden is to be fenced using a wall of a house as one side of the garden. The garden should have an area of 40 meters squared. Determine the dimensions that minimize the perimeter of the garden. If A, the dimension must be whole numbers. So it has to be whole numbers. Remember that the area we know is 40 meters squared, and that area equals length times width. So if I want to find ones that are whole numbers, I need to find numbers that divide into 40. So we could start with 40, but let's start with 20. We could then go to 10. The next number that would go into 40 is 8, then 5, then 4, then 2, and so on. The next thing to do is determine the width of these gardens. So if I chose the lengths, so 20, 10, 8, 5, and 4, the widths, if I look at my formula here, if I want to solve for the widths, I'm going to isolate by dividing both sides by L, the length, and that tells me that the width is equal to 40 divided by L, which I have here. So take the numbers that we decided will be the lengths, and if I take 40 divided by 20, I get 2 for the width of the garden. 40 divided by 10 is 4. 40 divided by 8 is 5. 40 divided by 5 is 8. And then 40 divided by 4 is 10. Now while these look the same, remember one side does not require a fence. So for the perimeter, I only need one length, shown here, but I need two widths, shown here and here, because one of the lengths does not need to be fenced. So let's look at the perimeter for each of these. So our perimeter formula says we have one length plus two widths. So if I take 20 plus 2 times 2, that tells me the perimeter of that garden is 24 meters. Keep going. 10 plus 4 times 2, that's the next row, is going to give us 18. So we can see there's even less perimeter. 8 plus 5 times 2, again, gives us 18. 5 plus 8 times 2 gives us 21, so we can see now it's going up. And then 4 plus 10 times 2 equals 24. So we can see to get the minimum perimeter, it's going to have to be one of these two constructions. So it's going to have to be 10 meters long by 4 meters wide, or 8 meters long by 5 meters wide. Therefore, the dimensions that minimize the perimeter are either going to be 10 by 4 or 8 by 5. So again, for this one, we have two answers. 10 by 4, 8 by 5 gives us the minimum perimeter of 18 meters. What if the dimensions can be decimals? Well, going back to part A, we see that a length of 10 or a length of 8 gives us the smallest perimeter. So somewhere in between should hopefully give us an even smaller perimeter. So let's say we choose the number 9. So let's start there. And then we got to figure out the width. So 40 divided by 9, that gives us 4.4 repeating. So let's say 4.44. And the perimeter for that is one length plus two widths. And that tells us we get a perimeter of 17.88. And then we can continue to check. So since we know it has to be between 8 and 10 based upon part A, we could check 9.5, 8.5, and so on. So let's just check 9.5 to see if it gets any bigger. So if we have 9.5, the width would be 40 divided by 9.5. That gives us 4.21. And if we check that perimeter, we can already see it's bigger. And we could do the same thing for 8.5 just to check. So this gives us 4.71. And that also gives us 17.92. This number here, 9, a length of 9 will give us the minimum perimeter. So the dimensions that minimize the perimeter, if we're allowed decimals, would be 9 by 4.44. And what that would look like is that these two sides would be 4.44, and this would be 9. And you can see that this is close to a ratio of 2 to 1. If you take 4.44 and double it, well, that's very close to 9. So the exact ratio is a 2 to 1 ratio. Alright, so let's try the last one. A rectangular garden is to be fenced using 900. Determine the maximum area if one side of the garden is against a house. So this time we want to maximize the area, and we note from before that it would normally be a square. But again, one side is fenced by the house, so we don't need fence against the house. So let's see what kind of shape we get here. So I've already started with some numbers, so I said let's start with a width of 100. And if we look at the perimeter for this question, so the perimeter equals, we have one length plus two widths. Right? Here's our two widths, here's our one length. If I want to isolate for length, since I know the perimeter is 900, To isolate for length, I'm going to minus 2 w's from both sides. And I end up with 900 minus 2w is equal to the length. So that's the formula I have up here. And remember, the area of a rectangle is length times width. So now let's sub in our numbers. So we start with 100. So 900 minus 2 times 100, that gives us 700. 900 minus 2 times 150, that gives us 600. And the area for these would be 700 times 100, so that would be 70,000. And the next one would be 90,000, so we can see the area is already going up. So let's check our next number. So let's go to 200. So 900 minus 2 times 200, that's going to give us 500. And you can see there that gives us 100,000. So our area is still going up. Let's try 250. And for 250, we get 900 minus 5, so that's 400. Again, we get 100,000. So we're hoping that the maximum area is somewhere in between 200 and 250, because they both give the same area. So somewhere in between. So let's check one more. Let's try 225. And for this one, we get 450. And then to get the area, that's length times width, we see we get 101, 250. So let's stop there and assume this is a good maximum area. So our dimensions we have are 225. So that, remember, is our width. So that's here. We have two of them. 225, 225. And then we see we have 450 for our length, which is a 2-to-1 ratio. Whenever you have one side that's not part of the equation, we're always going to end up with a 2-to-1 ratio of length versus width. And that was similar to the one we did above. Therefore, to get the maximum area of 101,250, we would need dimensions of 225 by 450. Here are 4 examples that you can try.